our another stability theorem we can use to justify whether the system is stable. And furthermore, this one will allow us to tell quantitatively how stable the system will be. Okay, and so far we have done for the stability, we have exercised is these and kind of try to brainstorming to see how many tools we've been available. The first one is we see all the roots of the characteristic equations on the left-hand side of the S-plane. So that is the number one rules we pick it up, right? So for stability. And the second tools we learned is using the Roots-Hurwitz criteria. From this criterion, we will be able to make tabulations, and from the tabulation, we ask, we can tell as long as the first column has no sign change, then that system should be stable. And we can also ask the first column has no sign change to find the value of the k, the range of the k value, and for the system to be stable. And anything else? I think pretty much there. Okay, so in this way, I would say the Nyquist stability theory will be our number 3 tools we can use. And so in the final test, on which I've been beginning to think about the problems, and I've been designing to ask you for stability and what is the range of the k value, and I specifically asking you to apply this theory and indicating if you use other approaches, no points will be given. Okay, so basically indicating at least one question will be from here, and you should know how to apply for it, so listen carefully. The Nyquist stability theory, let me give you the little bit background. Basically, that is based upon the in complex analysis, there's a theory called the conformal mapping. You don't need to know the detail, but you can simply pick up this terminology or key term. That should be good enough. Okay, I know in our curriculum, many of you might not have the chance to go to check the complex algebra with detailed complex analysis. But here, I will try. Basically, this stability theorem saying that consider characteristic equations. 1 plus and let me see. Okay, whatever the textbook using these notations. Okay. So this is the characteristic equations. Example of such system could be like this: G, H, and or G, H. Okay, so something the closed loop system would be making like this, or any, I would say in your applications or learning, you should say to generalize, not to be sticking with the form here I written. Maybe you can say, I would say for given any characteristic equations, I would say whatever E plus G. Okay, so whatever you don't be kind of confined with this one, but here I try to follow up the symbols from our textbook. So we consider the characteristic equations. So here is a given informations, and usually you know that, and in these characteristic equations, and here they will invent with certain design parameters, depends on the controllers. Okay, so these are open loop systems, these are controllers. So it depends on the controller you select. Usually there's a contents in the controller might have the, say, parameter k or if you select the PID, so now you have the P, KI, KP, and KD, whatever, right? Okay, just keep those things in mind. So here I'm writing in this way as kind of implicitly including those kind of the parameters already, okay? So that's the given systems, and we want to know is this, for stability. So for stability, that means we're asking this system to be stable. That means no root of the characteristic equations is on the right-hand side of the complex plane. Right? So basically, no root on the right-hand side. Basically, we stick with is our very original definition for stability. We know that one. So here the theorem says is this. I give you the equations first, and based on that equation, quite a bit of explanations I need to make. And so this equation basically is a simple equations, but is sometimes confusing, a little bit confusing for beginners to apply. That equation is saying n equal to z minus p, and let me explain these equations. N is this. The numbers of encirclement of the characteristic equations. And here, let me stick with the notations. So here, for example, 1 plus GH, okay? Or 1 plus G, okay? So that is the characteristic equations. The encirclement of the characteristic equations of the origin in the complex plane. So what is an encirclement? Let me explain this. So for example, if this is a complex plane, and again, given characteristic equations, this is the real part of the characteristic equations. Again, here I adopt the symbols for illustrations, but again, the symbol can be anything, as long as that is for describing the characteristic equations. So this is the imaginary part. Okay, so let you fill out those things. So again, do you know how to plot this? Yeah, basically this is a Nyquist plot of such a function, right? So this is a Nyquist plot of such a function. This function can be just a real example we just did it a few minutes ago. So once you plot it, and so for example, if your system would be something like this, okay? So say this one would be something like this. Then basically this origin is encircled in this one. So for this case, here I indicate the arrow of this encirculation. Basically here the n equal to 1. If the encirculation is opposite to this one, then n equal to minus 1. So we define the encirclement is in counterclockwise encirclement. Let me define the directions. Okay. And you might ask me, how do we know the directions of the encirclement? And later I will use one example to show you how to define it. Okay. So here we're simply using the encirclement CCW. Okay. And what is a Z? And Z is the numbers of zeros of the characteristic equations encircled by the Nyquist path, PATH. So here I introduce you another keyword, another terminology, Nyquist path. Nyquist path, okay? So here let me define you the Nyquist path. So in the complex plane, I would say the complex X plane, okay? And the Nyquist path is defined by this. Basically, the Nyquist path is a path. And encloses the entire right-hand side of the complex plane. So basically here we're using this one. So the radius equal to infinity. Okay. It containing the imaginary axis. Basically the whole the right-hand side has been encircled by this Nyquist path. And the Nyquist path is picking up by definition, the counterclockwise directions. Okay, so that is our sign convention for this path. Okay, so on the Nyquist path, we have so many points of the omega. So for example, omega 1, omega 2, and until say omega n, etc. And here omega n, omega n plus 1, etc., etc. So many data points we can sample from the Nyquist plot. So here, for consider given functions, for example, here these say 1 plus gh equal to 0, our characteristic equations. For example, here, let me say this one would be something functions. Characteristic equation, say, for example, I just make up like our previous example, s plus 1 and s plus 10, something, let me say 5, okay? So this is the equal to 0. So in this way, you can see here we can sample all the omega. We calculate omega 1, omega 2, omega n, and then omega n plus 1, until as happy as you like to pick, okay? Then you can calculate the g. So let me define this one. So how about say, let me define this is L over S. So you can determine the L over J omega. You can determine the magnitude and phase angle, right? So repeating our exercise, we can calculate those numbers, right? We can calculate those numbers. So basically here, then we plug into, so this is the real part of this particular functions, the transfer functions, and L, J omega. This is the imaginary of the L, J omega. Okay, so the exercise is very straightforward. And then, say, for example, omega 1 is here, omega 2, omega 3. So here, if you will be able to make a curve like this, so this indicates the directions of the encirclement. That means follow up the direction of the Nyquist path you define. Okay? So for this example, that really depends on the context of L. Again, the curve would be different, right? Okay, so for this case, that is defined, and for this example, so basically here that is the one here. So P here is again the numbers of the poles of something, the same thing here, okay? So P representing the number of the zeros and P representing the number of the poles here. Okay? Any questions so far? We're only halfway down about this explanation of this theory. Okay, so that is the way, and for stability, we asking is no roots of the characteristic equations. So what is the root of the characteristic equation? The basic that is the zeros of the characteristic equations, right? So for stability, we asking z equal to how much? Zero. Right? The statement of this one, no roots, that means no zeros. You know the definition of the zero and poles, right? Zero, that means the root of the numerators. The poles means the roots of the denominators. So that means for the root of the characteristic equation, basically that means the roots of the numerators, right? Okay, so for stability, that one we're asking z equal to 0 under such a choice of the Nyquist path. You good? So basically, in particular, for our Nyquist stability theorem, for stability, we're asking n equal to minus p. Good? Good? Okay. So this is the specific applications of, we call it the conformal mapping, or in control, we simply call the Nyquist stability theorem is this one. So this is simplified versions from a generic patterns, generic formula like this. Any questions? Good. Okay. Good. So now we can, if no further question, let me give try to scrutinize a little bit more information. For most of the control systems, let me make up one. So if this is an open loop system, say S plus 1, first order system, and you don't like this system, so here you can say put into say a constant, the constant gain on the feedback. Okay, so here I would say the examples of common control systems. And that could be, so let me say this is our G, and let me say this is over H, okay? So the common control system, G can be, say, the first degree, S plus P, the first order system, and can be second order system, I just make up, okay? And can be higher order systems. And the less common, so the H can be constant controllers, or it can be PID controllers, or anything, or lead or lag, anything you like. Right? For all the tabulated system here, I make look at the location of the poles. Their location of the poles are always on the left-hand side, right? And here, less common. So for those common control systems, and I would say the poles are all the poles are on the left-hand side, right? For most of the common system we've been seeing, we've been exercised, that is this case, right? Under these situations, that meaning is P per our definition, P equal to 0, the number of the poles on the right-hand side per our definition there in the stability. So that means in the framework of Nyquist stability theory, P equal to 0. Right? So under this case, for stability, that means Z equal to 0. So together the two things, we must ask in N must be equal to 0. Right? So this is the most common situations when we apply the Nyquist theory. That is this one. So that means when you plot the Nyquist, when you draw the Nyquist plot of a certain common characteristic equations, the origin shouldn't be encircled in your plot. So that is the implication of this result. Will be good? Okay, so from here you can see from this way to there, I gradually to simplify the theory. So this is the generic one. Then for stability, I simplify into this. And furthermore, for most of the common practical systems we've been exercised with, P equal to 0. So here I simply want to lay out the kind of big pictures of this theorem is. Okay, if you would have time, I encourage you to go there to read our textbook. And here I give you a warning. The contents of the textbook in this section is not easily being comprehended at the first time. So read through a couple times, okay? Not the way your knowledge is not enough. No, it's the way, there's no perfect textbook, but in my viewpoint, the writing in this textbook here is not user-friendly. Sorry about the authors, but that's my experience. Okay. Sometimes I got some comments, unless I disable the comments from the YouTube. But I'm really sorry, but that is my user experience. Okay, so if you have time and read through those things. So this is the big pictures, and any questions before I move on, because later I'm going to dig into more details, more quantitative description about this. Any questions before I address this? No? Okay, good. So again, here is the two levels of the simplifications to these common situations. So that one, for this case, the plot of the real J omega. So this is this one. Okay, I adopt, L, the imaginary of the L. So basically the plot should be something like this. Okay, so that is omega approaching to 0, omega approaching to infinity, and corresponding to our Nyquist plot, that is the infinity to 0 from 0 to minus. So here we make reflections, so that reflection is will be something like this. Okay. So for typical Nyquist plot of certain characteristic equations, it will be something like this. Basically, the origin is not enclosed yet. And here I'm drawing is very close kind of to the infinity, but later I'm going to show you in detail. I'm going to zoom in and to show you the origin shouldn't be encircled for such a scenario. Be good? Okay. And before I erase this, so this is the level 1 simplifications. And from here to there, that's the level 2 simplifications. So here I want to go up level 0, the generalizations. Okay. So this theory applied to, from the beginning, I picked the Nyquist path is to enclose the entire right-hand side. Because for our purpose, we concerned is whether we have any pieces of information, for example, the zeros on the entire right-hand side. So that is the area of the interest. So that means the Nyquist plot should be taken to cover the entire region of the interest. Okay. So the upper level going up to for generalized theory, the Nyquist plot can be anything you pick. Okay. In the original complex analysis, the Nyquist plot basically is on your choice. You simply pick a region of the interest. For example, again, so that is the real, and this is the imaginary. Okay, you can pick, say, like this. And of course, if you pick this region, then that means you try to investigate what is the influence of the complex number in this domain affecting to such your system behavior, like that one. Be good? Okay, so here again, here we have in total 3 levels of the in detail or in general applications. Again, for our stability in controls, we like to study is the picking this one entire right-hand side. But in general, from the complex analysis viewpoint, this path can be arbitrary. Good? If this path can be arbitrary, basically that makes another the possibilities for the number of n's and p. Good? Okay, so we can stop.